Welcome you all to Principles of Organic Synthesis. Presently we study molecular rearrangements. So far we had one lecture in this topic where we studied Wagner-Mirvin rearrangement, Pinacol rearrangement, benzylic acid rearrangement and homologation of carboxylic acids. In this lecture we will have three parts. The first part we will study the migration of halogen, oxygen and sulfur nitrogen based functional groups. Then we will see the migration towards electron deficient nitrogen atoms. At the end we will study the Baeyer-Williger and hydroperoxide based rearrangement reactions. This slide shows migration of oxygen, sulfur and nitrogen based systems. For example, if we have X which has a lone pair, as we have seen in the case of aromatic system, and it can assist as a neighboring group to cleave this carbon Y bond. So, you will be able to form a cation intermediate. So, if you have the X as a lone pair, for example, oxygen, here sulfur and here nitrogen, and they can assist the neighboring group, they can assist, so that this Y can leave with this bond pair, and you will be able to generate a cation intermediate. Once you form the cation intermediate, the nucleophile now can react. And if you have the symmetrical substrate, you will get the same product. If this whatever the cation intermediate that you generate is unsymmetrical, then the nucleophile try to react with the carbon which is a less hindered, less substituted carbon. So, therefore, there is a possibility of rearrangement in this reaction. Now, let us look at the first example. Here, when you react this substrate with aqueous silver salt, it can produce a silver bromide, for example, in this case, and then you will be able to form, and this cation intermediate, the lone pair can assist to leave this Br with its bond pair. You will be able to have this cation intermediate. Once we have this one, now you have two carbon. This is, if you look at this is more substituted comparing to that. So, therefore, this now water which acts as a nucleophile, it can react with the less substituted carbon via SN2 pathway, then you will be able to have this compound. So, what in this, if you look at here, and the removal of halogen can be carried out silver cation. Now, you can see here, and this can be assisted by the lone pair present in the oxygen. The methoxy group can act as a neighboring group. It can assist to leave this bromide with this bond pair. So, you produce silver bromide, you generate the cation intermediate. Once we have this one, now this unsymmetrical one, now this water can react with this carbon since it is less substituted, and you will be able to get this alcohol as a product. So, now let us look at this example as just we have seen here, and when you treat this alcohol with acid, for example, hydrochloric acid, and it can protonate. So, you will have this intermediate. Once if you form this one, this is the leaving group, you have the sulfur lone pair, it can assist and to cleave this carbon oxygen bond heterolytically, then you will be able to form this cation intermediate via SN2 pathway. Now, if you look at here, this carbon is less substituted comparing to that. Here you have the methyl group. Therefore, now the Cl minus whatever you generate, and this can act as a nucleophile. It can react this carbon predominantly comparing to that, because this is less substituted, less sterically hindered. Therefore, you will be able to have this alkyl halide having this thioether functional group. Now, let us look at this salt. When you salt treat with base, and you will be able to form this tertiary amine. Once if you have this one, and this lone pair of the nitrogen can assist and to cleave this carbon chlorine bond heterolytically. It can go with this bond pair and you will be able to form this cation intermediate. Once you form this one, it can act as a nucleophile now, can react with this carbon, and you will be able to open up this, and in this way you will be able to form this tertiary amine derivative. So, if you look at all this example, here you have the oxygen, here sulfur, here nitrogen with their lone pair, they can try to assist to cleave these leaving groups heterolytically. Therefore, you can generate the cation intermediate that can be further reacted with the nucleophile at the less sterically hindered carbon to give the substituted compound. Now, let us look at another example. The reaction of acetylenic alcohol is shown here. When you take this acetylenic alcohol, react with acid, as we have seen, you can try to protonate, and then you will be able to form. When you have water as nucleophile, you will be able to convert this alcohol into vinyl ketone as the product, and the mechanism of this transformation shown here. As we have seen, protonation of this triple bond can generate this carbocation intermediate. Once we have this one, then this can undergo reaction to produce this intermediate. Now, this can convert into this intermediate. This can tautomerize to this vinyl ketoenol. Tautomerization can lead to this ketone as the product. So, alternatively, this one of the possible pathway, if you have this acetylenic alcohol, alba acylic alcohol, when you treat with acid, and you can form this cation intermediate. Once you form this one, it can open up as shown here, and you will be able to form this intermediate enol. Once we have this enol, which can tautomerize to give this vinyl ketone as the product. Alternatively, it can also protonation of this alcohol can give this intermediate, which can lose water molecule, and you will be able to have a carbocation intermediate. Once we have this one, it can convert into E9. Once we form the E9, now this can now react with acid, protonation of this triple bond can produce this carbocation intermediate, which can now react with water, and you will be able to have which can lose proton, and you will have enol so which can undergo tautomerization as shown here, then you will be able to have this vinyl ketone as the product. So, there are two possibilities there. The triple bond undergoes protonation as shown here. This can be assisted by this lone pair of the oxygen. You will be able to have this cation intermediate. Once we have this one, it can assist of this, then you will be able to form this enol. This enol can be converted into ketone. Alternatively, protonation of this OH group can lose water molecule, and you will be end up with this tertiary carbocation, which can be converted into anion as shown here by removal of proton. Once if you form this anion, now among this electron rich which can undergo protonation here, addition with this proton, then you will be able to have this carbocation intermediate. Once you have the carbocation which can undergo reaction with your water molecule, you will be able to have this enol, which as just we have seen, and which can undergo tautomerization to give this vinyl ketone as the product. So, these are some of the examples. If you look at here, this tertiary alcohol here, when you react with the formic acid, and it can rearrange to this ketone, you can see here as just we have seen, and if you react with acid, protonation of this, you will be able to form this intermediate. Once if you have this one, now this you can open up and you will be able to have this can convert into so which can undergo tautomerization to give this ketone as the product. And similarly, in this case also, when you react this alba-acylic alcohol derivative with the formic acid, selectively this portion undergoes rearrangement, you will be able to get this ketone as the product similar to this substrate. And here let us look at this one. In this case also, when you react this substrate with the formic acid, and you will be able to get this compound in this reaction, as just we have seen. So, when you do protonation, for example, and you will be able to have this intermediate once you form this one, and this can in this system so removal of this proton, and then this migration takes place, and then you will be able to have This intermediate, which can just we have seen undergo ketoenol tautomerization to give this conjugated ketone as the product. So far we have seen example where you can see this oxygen, sulfur, nitrogen based functional group can undergo migration through neighboring group participation. It can make a cation intermediate. Once you form the cation intermediate, which can undergo reaction with the nucleophile, and we have seen some examples. Then we have seen the Roubaix rearrangement, where if you have the alpha acyclic alcohol, which can in the presence of acid can undergo rearrangement to produce vinyl ketone as the product. Now let us look at the reactions that involve rearrangement to electron deficient nitrogen atom. So the common intermediate in all these reactions will have these reactions will have this common intermediate. This is the leaving group. So if X is Br, then this will be Hofmann rearrangement. If X is N2, it can be Curtius and Smith rearrangement, and if X is carboxylate, then it can be Lawson rearrangement. So all these reactions we look at here, and they will have the common intermediate. Once you form this one, and this R group migrates to the electron deficient nitrogen, and in the case of Hofmann rearrangement, the leaving group X is Br. In case of Curtius and Smith rearrangement is nitrogen gas, and the case of Lawson rearrangement is going to be carboxylate. Now let us look at the Hofmann rearrangement. Here an example shown, the rearrangement of nicotinamide, the presence of sodium hydroxide, aqueous sodium hydroxide, and Br2 to give this beta aminopyridine. The mechanism of this reaction shown. In this reaction, the base hydroxide ion deprotonate, then you will have this intermediate. Once if you have this one, this can react with bromine, and you will be able to form this species. Once you form this one, it can further react with base. Deprotonation will be able to produce this intermediate. Once you form this one, this undergoes migration to here, and this can leave, and you will be able to form. You can also write like this. It can form the and you will be able to form this isocyanate. Once you form the isocyanate, it can migrate here. You form the isocyanate. Once you form this one, now if you have the nucleophile, the reaction medium, it can undergo addition reaction. For example, if you add water, can convert into a proton transfer. You can make once you form this intermediate, now it can lose carbon dioxide and you will be able to form this beta aminopyridine as the product. The reaction is regiospecific. You can see here wherever you have this the substitution where you convert this amide functional group into amino group and the same position, and this is the reaction pathway. For example, if you react with water and you produce the amine, you lose carbon dioxide. If you add another nucleophile, for example, here methanol. So, when you add methanol, you form this, and this can proton transfer can give this carbamate as a product. So, if you add methanol, you will be able to produce carbamate as the product, and this is now let us look at some more example. Here the mechanism of this reaction shown. For example, when you take this amide and when you react with aqueous sodium hydroxide, for example, it can deprotonate, then you make the unolate. You can see here, once you form this one, now it can react with bromine and you will be able to form this intermediate. Once you form this one, the base can again deprotonate this one and you form this unolate. Once you form this one, now this can undergo rearrangement, you will be able to form this isocyanate. Once if you have the isocyanate, now this reaction, just we have seen addition of water will be able to form this intermediate. Now proton transfer can lead to the formation of amine, and this one which can lose carbon dioxide, you will be able to form methylamine as the product. Here the reaction of methanol shown, the mechanism of this addition of this to isocyanate can give this intermediate. Proton transfer, as just we have seen, can lead to the formation of this carbamate. And on the other hand, if you add methylamine, for example, and in place of methanol, addition to the isocyanate can give this intermediate, and proton transfer can lead to the formation of urea as a product. So, this is a very useful reaction. So, isocyanate is the intermediate. Once you form this one, and you can try to react with the different nucleophile, that can lead to variety of compounds. So, here the substituent can be alkyl or aryl, and as we have seen that this also depends upon the nature of the substituent. The aryl system, the migration can be facilitated, as we have seen earlier. If you have the electron donating group, the reaction can be facilitated much greater reactivity comparing to that having electron withdrawing group. Now, let us look at this amide, benzamide. When you react with the NBS and base in methanol solvent, and you will be able to form this compound. Just we have seen the traditional Hofmann rearrangement, where they have used aqueous sodium or potassium hydroxide in the presence of bromine. Here N-bromosuccinamide has been utilized in the as and also used as this as base, this is DBU they have used. When you use the combination of this, as just we have seen, and you will be able to you can deprotonate this one, and you will be bromine you can add, as we have seen. Then again it can undergo isomerase rearrangement, and you will be able to form the corresponding isocyanate. Once you form this one, as we have seen just now, you can add methanol and you will be able to form this carbamate as the product. And here the reaction of phthalimide with bromine and aqueous potassium hydroxide is shown. As we have seen, this also now this portion is converted into amine as just we have seen, and you can deprotonation as we have seen, and addition to the bromine you will be able to have this intermediate which can convert into the corresponding isocyanate. Then when you add water, then you will be able to produce this androlinic acid as the product. Now, let us look at this amide. It has a chiral center. When you react this optically active one with the aqueous sodium hydroxide in the presence of bromine, and you will be able to form this amine with the retention configuration. As you can see here, the chiral center is intact under these conditions. So, just rearrangement takes place and this undergoes migration, and you will be able to get this amine as the product. Here another example shown, and so far we have seen all these reactions involve bromine based systems. Here chlorine based system is shown here, and this reagent of this TCCA is shown here, structure of this reagent. When you use TBU and this combination as just we have seen, and you can also convert this into the corresponding chloro derivative. Once you form this one, when you heat it, it will be converted into isocyanate. Once you form this one, when you add nucleophile like alcohol, you can generate this carbamate as the product. So, these are the example for now let us look at some example. In this case, if you look at here, this iodobenzene trifluorodiacetate has been used. When you react this iodobenzene trifluorodiacetate with this amide, acetamide, you will be able to form this intermediate. As we have seen, it can undergo reaction. This can leave as trifluoroacetic acid. You will form this intermediate. Once you form this one, which can now convert into isocyanate as shown here. Once you form the isocyanate, which can be further reacted with the nucleophile. And so, in place of as you can see here bromine, you can also use iodobenzene trifluoroacetate which can readily react with the amide. In this way, you will be able to form the isocyanate. And here another example shown, iodobenzene diacetate has been used this amide, which can be converted into amine using this, and here the combination of iodobenzene diacetate and potassium hydroxide has been used in isopropanol solvent to produce optically active amino alcohol as the product. So far we have seen Hofmann rearrangement, and we have seen the variety of examples and reagents that have been used for the transformation of amide to amine through isocyanate. Now, let us look at Curtius rearrangement, and if you have the acid chloride, you can try to react with the sodium acide and you will be able to form the acid acide. Once you form the acyl acide, and which can be written like this, resonance form of this. Once you form this one, this can, as we have seen, undergo migration as you can see here, and you can lose nitrogen molecule, you will be able to form this isocyanate. Once you form the isocyanate, as just we have seen the Hofmann rearrangement, and you can try to react with the different nucleophile. For example, you can react with the amine, you get the urea, you can write with methanol, you will get the carbamate, and similarly if you do with water, you will be able to get amine. And here the difference between this Hofmann and Curtius rearrangement is that in the case of Hofmann rearrangement, we have seen amide as the starting material. We react this amide with aqueous sodium hydroxide and bromine to give this isocyanate. Once you form the isocyanate, which can further react with the different nucleophile, here the starting material is acyl acide. Once you form the acyl acide, which can be converted into isocyanate by heating, and you will be, once you form this one, which can be further reacted with the different nucleophile to give the addition products. Here an application shown, and here the reaction of diethyl malonate with base is shown, which when you react with base hydrolysis can give this salt. Once you have this one, which can be further reacted with hydrazine, you can addition here, it can undergo addition reaction with this carbonyl group, and you will be able to form this hydrogen derivative. Once you form this one, which when you react with HNO2, and you will be able to form the acyl acide. Once you form the diazonium salt, and which when you react with acid, it can undergo decomposition and you form the nitrene. Once you form the nitrene, which can undergo now migration to give this isocyanate. Once you form this one, when you react with and water, then you will be able to produce glycine as the product. So, it is an example shown, and you can try to, if you have the diethyl malonate, you can use the Cartier's rearrangement, you will be able to transform to alpha amino acid as shown here, and hydrolysis of this ester can give this carboxylate salt. Once you form this one, and which can now further undergo reaction of the hydrazine, you form this can be reacted with the HNO2 as we have seen earlier. You can form the acyl acide. You have to control the temperature as we have seen. Once you form this one, you have the acyl acide, which when we react with acid, it can convert into isocyanate, and which can be further reacted with the water and followed by removal of carbon dioxide, you will be able to form glycine as the product. Similarly, you can try to make other amino acids. Here another example shown, the reaction of this carboxylic acid with acid chloride can generate reaction of the carboxylic acid with oxalyl chloride can generate the corresponding acid chloride. Once you form this one, when you react with sodium acide, so once you have the acyl acide as we have seen, and when you heat, you can give the nitrene, which can undergo now rearrangement, you will be able to form the isocyanate. Once you have the isocyanate, which can now you can have the benzyl alcohol, you can try to do addition reaction, you will be able to get this compound, which has been further converted into complex molecule, which is very important in medicinal chemistry. Here another example shown, and here the reaction of benzoic acid with this polymer supported acide is shown, and which can be converted into acyl acide. Once you have the acyl acide as we have seen, and which can be further converted into isocyanate, that can be reacted with ethanol, you get this the corresponding carbamate as a product. Here also the reaction of this acid shown, when you react with the oxalyl chloride, you will be able to form the corresponding acid chloride. Once you form the acid chloride, which can undergo reaction with the sodium acide, you make the acyl acide. Once you form the acyl acide, as we have seen, which can be converted into isocyanate by removal of nitrogen molecule, and once you form the isocyanate, that can further undergo reaction with this amine, you will be able to make this urea derivative as a product. So far we have seen the Hofmann and Curtius rearrangements. Now let us look at Smith rearrangement. Here, as you can see, the reaction of carboxylic acid shown when you react with HCN3 in the presence of acid, and you will be able to form amine as the product. In this reaction, see the protonation of this carbonyl group can give this intermediate. Once you have this one, which can undergo addition reaction with this HCN3, then you will be able to form this intermediate. Once if you have this one, and it can lose water molecule, it can convert into, it can lose water molecule, and you will be able to form this acyl acide. Once, as just we have seen the case of Curtius rearrangement, once you form the acyl acide, I already know that So, you can when you heat it, it can lose nitrogen molecule, you will be able to form the isocyanate. Once you form the isocyanate, you can react with the water, you will be able to form amine. So, if you look at the Curtius and Smith rearrangement, they have similar, and if you form both involves the acyl acid. In the case of Curtius rearrangement, you have the acid chloride, you react with sodium acide and you form the acyl acid, which has been further converted into isocyanate by removal of nitrogen molecule. When you heat or when you react with acid, it can lose nitrogen molecule, you will be able to form the nitrogen, which can undergo rearrangement to give the isocyanate. Here the acid has been reacted with HCN3 in the presence of acid, then you will be able to form the acyl acid. Once you form the acyl acid, since you carry out the reaction in the presence of acid, it can readily undergo rearrangement to isocyanate by removal of nitrogen molecule. And once you form this one, which can be further reacted with amine, for example, or any nucleophile to give the addition product. So, if you take for example, just we have seen the reaction with carboxylic acid. If you have the carboxylic acid, you can try to react with the HN3 in the presence of acid to give the acyl acid. Alternatively, you can also try to react with other carbonyl compound. For example, here the reaction of ketone is shown here, as we have seen, and if you have the ketone, that also can readily undergo reaction with acid, you can protonate this carbonyl group, you will have this one, and now is more electrophilic nature, which can readily undergo HN3, and you will be able to have you will form lactam as the product. The presence of acid, you can protonate, you will be able to form. And similarly, if you have, for example, in this case the reaction of this ketone shown, this ketone has which you have seen, and in the presence of trifluoromethane sulfonic acid, you can try to protonate. Once you form this one, and you have the sodium acid, which can undergo addition reaction, and as we have seen, you will be able to form the addition product. And since you carry out the reaction in the presence of acid, it can readily undergo decomposition to nitrene by losing nitrogen molecule. Once you form the nitrene, now it can undergo rearrangement as shown here, and you will be able to form the lactone. In this case, you will be able to form the amide as the product. Here another example shown here, also the reaction of this ketone with sodium acid is shown in the presence of methyl sulfonic acid. You can get this amide as a product, and similarly here also the reaction of this ketone with HN3 in the presence of sulfuric acid here, as we have seen, and you will be able to form this lactam as the product. So, if you remember the difference between the Curtius and Smith rearrangement, in the case of Smith rearrangement, you can also use ketone as the substrate, whereas in the case of Curtius rearrangement, we use the case of Curtius rearrangement, we have seen the use of acyl acid as the starting material, whereas in the case of Smith rearrangement, you can try to use ketone as well as the carboxylic acid to form the isocyanate, and once you form the isocyanate, which can be further reacted with the nucleophile to give the corresponding addition product. Now, let us look at the Larsen rearrangement. The difference between the previous and this one, here you can see, and this amide derivative has been used as the starting material, and this can be made if you have this hydroxylamine derivative. When you react with, for example, in this case, react with this acid anhydride, and which can undergo addition reaction, you will be able to form this intermediate. This is the starting material in this case. Once if you have this one, when you react with base, deprotonation can give this intermediate. Once if you have this one, now this can form this enolate. Once you form this enolate, now this can migrate, and this can act as a leaving group, then you will be able to form this isocyanate. Once you form the isocyanate, which can be further reacted as we have seen with the variety of nucleophile, and to give the corresponding addition product. For example, if in this case the reaction of water is shown, once if you use water as a nucleophile, you will be able to produce amine as the product. Here some examples are shown, and here for example, in the case of this hydroxylamine derivative can be reacted with toluene sulfonic acid, and so in the presence of base you will be able to form this isocyanate, which can be further reacted with water, and you get this aniline. On the other hand, if you react with this dimethylamine, you will be able to get this urea derivative. Similarly, here the reaction of carboxylic acid is shown, which can be reacted with the hydroxylamine. As we have seen, you will be able to form this kind of hydroxylamine derivative. Once you form, when you react with the phosphoric acid, and you will be able to form the isocyanate, and the base also is needed, and you will be able to form this naphthylamine. Similarly, here the reaction of aliphatic carboxylic acid is shown, which can be reacted with the hydroxylamine to produce this derivative. Once you form this one, which can be further converted into the isocyanate, and using this condition phosphoric acid and base, and you will be able to form the alkylamine as the product. Here another example shown, this hydroxylamine derivative can be reacted with this carbonate, dimethyl carbonate, in the presence of this base in dichloromethane and methanol solvent, you will be able to get this carbamate. And similarly, here this hydroxylamine derivative in the presence of diethyl azo dicarboxylate, the phosphine. So, Mitsunobu reaction, you will be able to form this oxazolic derivative, which can be further converted into this complex molecule. Here another example shown, and once you form this derivative, and here once you have the hydroxylamine derivative, which can be further reacted with phenyl sulfonyl chloride, you get this intermediate. Once you have this one, when react with the base, and you will be able to form this carboxylic acid. Similarly, here the reaction of this hydroxylamine derivative shown, when you react with this urea, and then you will be able to get this heterocyclic scaffold. And so far we have seen the migration to the electron deficient nitrogen, where first we have seen the Hofmann rearrangement, where if you remember, we use amide as the substrate. When we react the amide with aqueous sodium hydroxide in the presence of bromine, you will be able to convert into amine. That if you remember, the reaction involves isocyanate as the intermediate. And then we have seen the Curtius rearrangement, where we use acyl acid as the substrate, that also convert into, when you heat, it can convert into nitrine, which can rearrange to isocyanate, which can be further reacted with the nucleophile. Then we have seen the Smith rearrangement, where we use carboxylic acid or ketone as the substrate. When you treat this substrate in the presence of acid with HN3, you will be able to form the acyl acid or the corresponding acid derivative. Once you have this one, which can also be readily converted into isocyanate, since you carry out the reaction in the acidic medium. Then we have seen the Larsen rearrangement, where you use the hydroxylamine derivative. When you have this one, this in the presence of base can be converted into isocyanate. Once you have the isocyanate, which can be further reacted with the different nucleophile to give the corresponding addition product. If you remember all the reactions, and if in the case of Larsen rearrangement, there is a limitation, since you do not have a lot of hydroxylamine derivative, and so the substrate scope is limited in the case of Larsen rearrangement. When you go for the Smith rearrangement, since you carry out the reaction in the acid medium, if you have the acid sensitive functional group, they also have limitations, and when you go for Curtius rearrangement and you have to make acyl acid, once you make the acyl acid, the reaction can be efficiently carried out. And when you go for the Hofmann rearrangement, you do not have that problem, and you can try to, if you have the amide, you can try to react with aqueous sodium hydroxide or potassium hydroxide with bromine, then you will be able to convert into the corresponding amine derivative. And also, if the substrate has base sensitive functional group, then you have to use the corresponding rearrangement to get the desired products. Now, let us go for the Beckmann rearrangement here, and here the oxime is shown here. Oxime undergoes rearrangement in the presence of acid to give the amide as the product. This reaction has wide application. You can see here, for example, if you have this oxime, and which when we react with the sulfuric acid, you will be able to form the caprolactam, which is the precursor to make nylon. And when you heat, and you will be able to make nylon, and this reaction is stereospecific. And when you treat with acid, this trans to this leaving group undergoes migration, you will be able to get this compound. The mechanism of this reaction shown, protonation of this can give this intermediate which can lose water molecule. You will be able to form the cation intermediate. Once if you have a cation now which can react with the water molecule, and you will be able to have this amide as a product. And for example, here also given here, when you take the cyclohexanone react with hydroxylamine, you make the oxime, and when you react with the sulfuric acid, and you will form this intermediate. Once you form this one, now this can migrate, and so you will be able to have this carbocation intermediate which can react with the water molecule. Addition reaction can give this, which can isomerize to this caprolactam as the product. And here some examples shown. For example, in this case, and as we have seen, when you react with sulfuric acid and followed by, you can undergo migration, you will be able to get this lactam as the product. And for example, in this case, this can undergo migration, and you will be able to get this substituted caprolactam as the product. Here again shown in this case, and this aryl ring undergo migration because this is trans to this OH group, and you will be able to get this amide as a product. As you can see here, the reaction is stereospecific. The substance which is trans to the OH group undergoes migration, and you can get this corresponding rearranged product. And if you look at here also, if you take the reactivity of the substituent, the aryl substituent shows greater reactivity comparing to the alkyl substituent. And if you compare the reactivity of different aryl group, the aryl group that has donating group shows greater reactivity comparing to that having electron withdrawing group. This because this clearly shows that if you try to remember, so earlier case, this may be this acts as a neighboring group in this case, and you can try to, as we have seen, and assist to form the arenaceum ion intermediate by neighboring group participation. Once you form this one, now this can migrate to this nitrogen, and this may be the responsible. When you have the electron donating group, the reaction is accelerated comparing to that having electron withdrawing group. And if you see the reaction of aryl group, which shows greater reactivity comparing to the alkyl group, which clearly shows that this may be due to the neighboring group participation of this aryl ring that can facilitate this heterolytic cleavage of this nitrogen and this oxygen bond that can convert into the corresponding carbocation intermediate, which can further react with water molecule to produce the amide as the product. Here another example shown here, the reaction of this oxime with the PCl5 in the presence of acid shown. As we have seen, just this can undergo migration, you will be able to get this lactam as the product. And here if you look at, in this case, the polyphosphoric acid has been used, and this also you can undergo migration as shown here, you will be able to get this compound. And here again, when you react with phosphorus pentoxide, as we have seen, so it can migrate and then you will be able to get this bicyclic lactam as the product. The next reaction involves the rearrangement to electron deficient oxygen. Here the Baeyer-Villiers reaction shown when you have the ketone, for example, when you react with metachloroperbenzoic acid, so when you react with metachloroperbenzoic acid, it can produce this ester as the product, and you can also try to react with the hydrogen peroxide in the presence of base, and it can also produce the ester. And the hydrogen peroxide, when you treat with base, you will be able to generate this nucleophile, which can undergo addition reaction followed by rearrangement to give this ester. Now let us look at here the mechanism shown, and this can undergo addition reaction to this carbonyl group, and we will have this intermediate. Once we have this one, this group can migrate here and you will be able to form this product. If you look at among these, this is migration of this group is more favored comparing to that. This is because of this more nucleophilic, it can undergo migration to the electrophilic oxygen, and then you will be able to get the ester as the product. This reaction mechanism in case of base catalyzed reaction, when you have the hydrogen peroxide in the presence of base, and you can try to react with the ketone, form the ester as a product. Now let us look at the acid catalyzed reaction. For example, if you have the metachloroperbenzoic acid and protonation of this carbonyl group, as we have seen earlier, you will be able to form this intermediate. Once you form this intermediate, now this can now undergo addition reaction. This will be able to form this intermediate. Once you form this one, now this can now migrate here, and this can go here, and this can pick up this proton. Then you will be able to form. You will be able to form. You can write like this also. You can, once you form this one, now you can form this intermediate. Once you form this one, now it can migrate as. So this can undergo addition to this, and then you will be able to have this intermediate which can lose proton. Then you will be able to have this intermediate. Once you have this one, protonation of this carbonyl group can generate this intermediate. Once you form this one, and this can undergo migration shown here, this will come here, and this you will be able to form this ester, and you generate metachlorobenzoic acid, the byproduct, which can lose proton. Then you will be able to form this ester as a product. Alternatively, you can try to also write, once you form this one, and this also, now this can migrate as shown here, it can go here, then this can lead, and this can also pick up the proton. In this way you will be able to form this which can lose proton. Then you will be able to form this ester as the product. Here the rearrangement of this bicyclic ketone shown. When you react with the metachlorobenzoic acid, reaction usually carried out in dichloromethane, and if you look at here, the oxygen insertion takes place this carbon, because if you look at this one, and this is more nucleophilic, and therefore when you form So, now this, since this is electrophilic oxygen and this is more nucleophilic comparing to this carbon. Now, this carbon or this carbon can migrate. If you compare the nucleophilicity of this carbon and this more nucleophilic, it can migrate here, and so this can be facilitated by this. Once migrate here, this can come here, this can pick up this proton, then you will be able to form this lactone as the product. Similarly, in this case, if you look at here and you have this carbon and this one, this is more nucleophilic, this can undergo migration and to give this bicyclic lactone as a product. Here the metachlorobenzoic acid has been used. Here the combination of hydrogen peroxide and acetic acid has been used, and you also will have a similar kind of, in this case maybe the acetic acid is oxidized to peracetic acid, which acts as an oxidizing agent which can undergo reaction, and you will be able to form this bicyclic lactone as the product. Here an application shown, the synthesis of L-TOFA here, and this amino acid can be here. So, the first here acylation of this aromatic system can give this derivative, the presence of aluminum chloride. Once you form this one, when you try to oxidize the presence of sodium hydroxide, as just we have seen, which can undergo addition reaction with this ketone, and then you will be able to form this ester. And once you form the ester, you can do the hydrolysis, and in this way you will be able to introduce hydroxy group. And you can see here, if you have this tyrosine can be converted into this amino acid. You can try to introduce OH group. What you do here, do the acylation, Frelich-Graf reaction, you will be able to form this ketone. Once you have this one, you can try to use this oxidation reaction using hydrogen peroxide in the presence of base. You can convert into the ester. Once you have the ester, you can do the acid hydrolysis, and you will be able to make this L-TOFA as the product. Here the reaction of this ketone, bicyclic ketone, with trifluoroper-acetic acid is shown here, and you can here the oxidation of this bicyclic ketone here trifluoroper-acetic acid is shown here, and you can convert into the corresponding lactone. You can see here, and among this the oxygen insertion will take place. As we have seen, this is a more nucleophilic, and you can undergo rearrangement. You can try to introduce oxygen selectively, as just we have seen. And here the reaction of this bicyclic ketone with metachlorobenzoic acid shown among this, and this can undergo migration, and you will be able to introduce oxygen atom. You will be able to form the bicyclic lactone. And similarly, in this case also here, since this more nucleophilic, now this oxygen insertion takes place here, and you will be able to form this lactone as the product. And here the hydroperoxide rearrangement shown. And also, if for example, this is a very important industrial process to prepare phenol. If you have the cumene when you react with oxygen, you will form the cumene hydroperoxide. Once you form this one, when you react with the acid, as we have seen, protonation of this, as you can form this. Once you form this one, now this can undergo migration, and this can lose water molecule. You will be able to form this carbocation intermediate, which can undergo reaction with water. You will form the addition product, and once you form this one by proton transfer, and you will be able to cleave this bond. As you can see here, protonation cleavage of this can lead to the formation of phenol and acetone as a product. This is very common method to prepare phenol and acetone from cumene. When you react with the oxygen, you form the hydroperoxide. When you react with acid, you will be able to convert into phenol and acetone as the byproduct. And here the reaction of this hydroperoxide and cyclopentyl hydroperoxide is shown. The presence of acetic acid, you can convert into cyclopentanone and phenol, as just we have seen the rearrangement of cumene hydroperoxide. and similarly here this hydroperoxide also in the presence of acid can be converted into phenol and acetone as a product. And this, as we have seen earlier, there is a possibility of this can involve as a benzonium ion intermediate as shown here, and to facilitate this transformation. Here the reaction of aldehyde with hydrogen peroxide in the presence of base is shown. Once if you have this one, as we have seen, it can undergo addition reaction. As you can see here, addition reaction can lead to the formation of this, and which can rearrange as shown here, and you will be able to form this intermediate. Once if you have this one, which can further react with the base, and you will be able to get the addition product which can undergo heterolytic cleavage as shown here, and you will be able to form the catechol in this process. Suppose if you have the salicylaldehyde, when you react with hydrogen peroxide in the presence of base, it can lead to the formation of catechol as the product. And here this ketone rearrangement of this ketone shown, as we have seen, when you react with hydrogen peroxide and sodium carbonate, you will be able to form 1,2-dihydroxybenzene as the product. Similarly here the rearrangement of this para-hydroxybenzolate is shown. When you react with this urea hydrogen peroxide, this is also commercially available. As we have seen, it can also undergo rearrange. You will be able to form the 1,2-dihydroxybenzene as the product. In summary, today we have seen the first part, we have seen the rearrangement of oxygen, sulfur, nitrogen base systems, and they can try to rearrange, they can assist the heterolytic cleavage of the leaving group. In this way, you will be able to form the rearranged product. Then we have seen the reactions that involve a rearrangement to electron deficient nitrogen atom, where we have seen the Hofmann, Curtius, Smith and Lawson rearrangement. All this rearrangement involves isocyanate as the intermediate. In the case of Hofmann rearrangement, the starting metal is amide, which reacts with bromine in the presence of sodium hydroxide to produce isocyanate, whereas in the case of Curtius rearrangement, the starting metal is acyl acide. If you have the acid chloride, you can try to react with the sodium acide, you will be able to form the acyl acide, which when you heat and it can convert into isocyanate, you will form the nitrine, which can now undergo rearrangement to give the isocyanate, whereas in the case of Smith rearrangement, the starting metal is carboxylic acid or ketone. Once if you have the carboxylic acid in the presence of acid, they can undergo protonation and followed by reaction with HN3, you will be able to form the acyl acide. Once you form this one, since you carry out the reaction in the acidic medium, which can readily lose nitrogen, you will be able to form the nitrine. Once you form the nitrine, which can rearrange to isocyanate, whereas in the case of Lawson rearrangement, you use hydroxylamine derivative. Once you form the hydroxylamine derivative, which can be reacted with acid anhydride, you form the corresponding ester derivative. Once you form the hydroxylamine derivative, this can be further reacted with the presence of base to convert into isocyanate, which that can readily undergo reaction with the different nucleophile to give the corresponding addition product. Then we have seen the Beckmann rearrangement. If we have the oxime in the presence of acid, they can readily undergo rearrangement to give the lactam as the product or amide as the product, which find broad utilities. For example, you can try to use this method to prepare caprolactam. Once we have the caprolactam, which we use as a precursor to make nylon, find broad utilities in chemical industries. Then we have seen the Peyer-Villiger rearrangement. If you have the ketone as a starting material, you can try to react with the metachloropyr-benzoic acid. For example, you can try to convert into lactone, or if you have the acyclic ketone, you can convert into ester. And also we have seen some examples. You can also try to use hydrogen peroxide in the presence of base to make a similar product. So we have seen the mechanism for both the reactions. They also find broad utilities. If you have the ketone, if you want to convert into ester, and you can use these methods, and this reaction can be carried out on mild reaction conditions. Then we have the Tachin reaction. If you have the ketone or aldehyde, you can try to react with hydrogen peroxide in the presence of base. You can convert into the hydroxy compound. We have seen some examples. All these reactions are often used in the laboratories to they find broad utilities. With this, we conclude this lecture. Thank you very much.